a derivative? Okay. Let me go ahead and do this just in case. All right, so the next 2 days, well, for the next like 4 weeks, we're going to spend on what a derivative is. But specifically today and Monday, we're going to focus on the definition of it. So here we go. What is a tangent line? A tangent line is a line that intersects a curve at only one point. If you think back to your days in geometry, right? You talked about secant lines and tangent lines. Tangent lines intersected your circle once. Secant lines intersect your circle how many times? Twice. Okay. Okay, so this word derivative, it is going to have a few synonyms. Okay? Synonyms, words that have different meaning, or same meaning, excuse me. Different words, same meaning. So our first synonym for derivative is instantaneous rate of change. The instantaneous rate of change of a curve means we are finding the slope of the tangent line. Okay, so our first synonym, instantaneous rate of change. When you hear rate of change, what do you think of? Slope. Okay? So we're finding slope, but we're finding it at a specific instant. Okay? Lines have slope. Okay? Parabolas, they don't have slope. Alright? But what we can do is we can find the slope at the coordinate 1, 1. And we can find the slope at the coordinate 2, 4. Different slopes, but at that instant we can find slope. And at the instant where x is 5, we can find slope. Okay? Well, how do we do that? Let's think of this picture. And you don't necessarily need to draw this picture. I'm just going to take you through a series of pictures to show you what's going on. What I'd like you to do is I would like you to write this limit right here. Okay? The limit as x1 approaches x naught of f of x1 minus f of x naught over x sub 1 minus x. Write it down and then we'll talk about what that is. So here is x naught right here, okay? And I have drawn a secant line through these two x coordinates. And what is this limit saying? This limit is saying x1 is going to, well, as x1 approaches x naught. So what we're going to do by evaluating this limit, we're going to bring x1 closer and closer and closer to x naught. Okay, right? That's what's happening. So watch my picture. As we take the limit as x1 approaches x naught, okay, those 2 points get closer and closer together until what's going to happen? Until we get our tangent line. All right? Now, let's talk about this right here. What is this? It's slope, right? So, over here we have the slope between the secant line. As we bring those 2 points closer and closer together, that slope is calculating the slope of the tangent line, which is our instantaneous rate of change. Okay? Let me give you another picture. Okay, does that look familiar? Yes, what was this? The difference quotient, okay? F of x plus delta x. That is the y value right here. Minus f of x. That's the y value here. All over delta x. Okay, let's think about this. Y minus y over x minus x. That's what we talked about over here. And you said that was the slope, right? The difference quotient is just another way of writing slope. Difference in y's over, instead of difference in x's, it's just labeled as change in x, right? In science class, you know that delta means change in x. Okay, so essentially we have the same thing. We have the limit as our change in x approaches 0 of slope. Okay, so as the change in x approaches 0, which means these points get closer and closer and closer together until we have a tangent line. Okay, so what's happening here is when we're taking the limit of the difference quotient, what are we finding? What about the tangent line? The slope. The limit of the difference quotient is actually calculating the slope of the tangent line. I just told you something about the slope of the tangent line. I told you that it was what? The instantaneous rate of change. And the instantaneous rate of change is the derivative. So the derivative, right now, the only thing you know about a derivative is that it's the limit of the difference quotient. Okay. The limit as delta x approaches 0 of the difference quotient. It is calculating the slope of the tangent line, which is the same thing as the instantaneous rate of change at a point, which is the derivative. So I couldn't really tell you that what you were doing in Unit 1 because you didn't know what a derivative was. But all those limits that you had to do with the difference quotient, you were really finding a derivative. You just didn't know. Now, that can make you frustrated or happy, either way. But the work that we are going to do today, you've done it before. You've taken that limit before with various functions. That's really all I'm going to ask you to do today. It just now has a different meaning. Okay? Now, let's read this again. A derivative is the slope of the tangent line, which is also the instantaneous rate of change. You need to be able to take those three meanings and interchange them. Instantaneous rate of change, slope of the tangent line, derivative. They all mean the same thing. So when you read one of those three things, you need to understand that it means the other two. If you read derivative, slope of the tangent line, instantaneous rate of change, slope of the tangent line. Okay? You read slope of the tangent line, I need the derivative. Okay? Those you need to be able to interchange and understand their meaning. Okay, so what I'd like to do first is I'd like to go through an example of finding the derivative. We're going to go through the difference quotient limit, right? And then I want to talk about what that means graphically as far as our equation goes. So what I want to start with is the equation f of x equals x cubed plus 3. Okay, now I got really excited and I failed to mention something, so give me one moment. Did you guys notice this notation right here? When we talk about the derivative of f, we call that, sometimes you'll hear me say like f prime of x. That little prime superscript, that means derivative. So I read this as f prime of x. That means derivative of f. Okay, that notation I did not point out because I was so excited to do a limit. I apologize. Can you see it? Just kind of like a apostrophe, kind of what it looks like. Okay, so our function is x cubed plus 1. Find the derivative, so we are calculating f prime of x. And we're going to do that by taking the limit of the difference quotient. Now, same thing as back in Unit 1. If you prefer to use h's, go for it. All right? Delta x, sometimes we see an h there instead for height. That is totally fine. If you want to use h, you can. All right, so f of x plus h means we're plugging, f of x plus delta x. We're plugging x plus delta x into our function. We are then subtracting our function. Ooh, this is funny. Sorry about that. I got a little distracted. Please do not forget that when you're taking the difference quotient, when you're setting it up, and you are subtracting f of x, you want to subtract f of x in its entirety. So I put it in parentheses there. Okay? Okay, we know that we need to do some algebra before we can evaluate the limits. Okay, because we have a 0 in the denominator. Okay? A binomial cubed. Okay? You can either multiply the 3 out, or you can remember Pascal's triangle, 1, 3, 3, 1. Right? So we have x cubed plus 3 x squared delta x plus 3 x delta x squared plus 1 delta x cubed. That would be the expansion of the binomial to the third power. Okay? Don't forget that we still have this plus 1, and we are subtracting x cubed plus 1 in its entirety. Okay? So now let's go ahead and reduce this down. What happens? X cubed cancel and our 1's cancel. Basically anything that doesn't have a delta x goes away. Alright, so we are left with 3x squared delta x plus 3x delta x squared plus delta x cubed all over delta x. Okay? Notice how all 3 terms in our numerator have a delta x in common. Okay, let's think about factoring it out and simplifying down, right? we're going to be able to reduce those delta x's because we have a delta x in the denominator. To save some space, we're going to do that and simplify all at once. So if we factor out a delta x and cancel it out with the denominator, we are left with 3x squared plus 3x delta x plus delta x squared. Now we evaluate the limit. Where do we plug in 0? For delta x. So to evaluate our limit, we're plugging in 0 for delta x. Which means, what are we left with? 3x squared. It is good if you have an x in there, okay? It is going to be some sort of an equation. I will tell you the only time you won't have an x appear in your derivative is when you're taking the derivative of a linear function. You're going to get a constant because a linear function has constant slope. Okay? So, the derivative of x cubed plus 1 is 3x squared. Okay? What does that mean? You told me, Mrs. Holman, that this represents the instantaneous rate of change. It represents the slope of the tangent line. Let's talk about what this means. Okay? So let's think about our graph. And this is not going to be like my most spectacular graph, but we'll make it work. X cubed plus 1. Do you agree with my graph? Okay, thank you. We found our derivative to be 3x squared. So let me ask you this. What is our derivative at 0? If I plug in 0 to the derivative, what do we get? We get 0. Which means at x equals 0, we have a tangent line that has slope of 0. Okay, that makes sense. It kind of flattens out right there. All right. What would our derivative be at -1? 3. So that means when x is -1, our tangent line would have a slope of 3. F prime of 2 would be 12. That means at 12, at 2, we have a slope of 12 if we were to draw a tangent line. That is what it says. Okay? So we have an equation that can give us the instantaneous rate of change at whichever point we would like. Let's talk about times where we cannot find a derivative. Okay? So a function is what we call differentiable at a point if the derivative exists there. So a function is differentiable if the derivative exists. A function is differentiable if the derivative exists at that point. So we're going to go through some examples of non-differentiability. It's a big word to say. Okay? What does it look like if we are not differentiable? Okay? Here are 3 cases. Anywhere where we are not continuous, we're not differentiable. Okay? So if we are continuous, if we are not continuous, we are not differentiable. Vertical tangents have undefined slope, right? If we were to draw a tangent line that was vertical, it would have undefined slope. That would mean an undefined derivative. So the derivative does not exist when we have a vertical tangent. And then we are also not differentiable if we have a corner. Sometimes you will hear them called a cusp. If there is a corner, we are not differentiable. Okay. Now, Unit 1, we talked about a lot of different kinds of discontinuity. Remember, asymptotes count there, jumps, holes. If there's any sort of discontinuity, not differentiable. Vertical tangency, not differentiable. Corners, not differentiable. Okay, I want to talk about the corner ones specifically. We have a very basic parent graph that has a corner. What is it? Absolute value of x. Where would the absolute value of x not be differentiable? 0. Okay. I'm going to give you a fun little fact. Okay. If y, so if f of x is the absolute value of x, fun fact, the derivative is the absolute value of x over x. Okay, I'm not going to go through the algebra for that. I'm just going to tell you. What does that graph look like? Okay, hole at 0 going to the right, or at 1, 0, 1, hole at 0, negative 1 going to the left. If this is the derivative graph, there's not even an x value at 0, right? Okay? We are not differentiable. The derivative does not exist at 0. Okay? It's kind of nice to see where that actually comes into play, right? All right. So here would be, you don't have to write this down, but here would be an equation, y equals x to the 1/3, okay, right, the cube root. We have vertical tangency, okay. If we try to find the limit of the difference quotient for x to the 1/3, we're not going to be able to get a value. It's not going to exist. Anywhere with the vertical tangency, no derivative, okay. Okay, here is something that you need to know. If f is differentiable, then we know f is continuous. We saw up there on that slide a couple minutes ago that if we were not continuous, then the derivative couldn't exist. So if the derivative does exist, we know that that condition of continuity had to have been met. Okay? So if we can find the derivative at that point, we know it's continuous there. All right, some notation. Oh, sorry. The converse is not always true. If continuous, then differentiable. Can somebody give me an example of a graph that is continuous but not differentiable? Absolute value of x. Anytime we have a corner, right, we could be continuous but not differentiable. Okay? Well, Some notation. I already told you about f prime of x. If you have an equation that's like y equals something, you could see y prime be notation for your derivative. Another very popular one, dy dx. It's basically saying change in y over change in x. dy dx. You'll see me use that quite a bit throughout the year. And then this one, d dx of f of x, this is saying, hey, find the derivative with respect to x of what's inside. Okay, so when you don't see like the dy dx, it's basically saying take a derivative with respect to this variable of whatever is next to it. All right, so we're going to do one more example, and then I'll give you your gold sheet so you know the schedule for Unit 2. Okay, please write down y equals x squared plus 1, and please write down the coordinate 310. Okay, so the first thing I'm going to ask us to do is find the slope of the tangent line. What do we need? The derivative. All right. So the derivative, I'll call it y prime, is the limit as delta x approaches 0 of, okay, x squared plus 1. So x plus delta x, the quantity squared, plus 1 would be f of x plus delta x, minus the function in its entirety, all over delta x. Okay, so when we take that binomial squared, we have x squared plus 2x delta x plus delta x squared plus 1. Then we are going to subtract x squared plus 1. This should happen. Anything without a delta x should be able to cancel. Okay. In the interest of saving room on my slide, we can all tell that these have gone away, and we have two terms left, correct? Both of which have what in common? Delta x. So we can reduce this down to 2x plus delta x. Do you agree if we divide each of them by that delta x term? Okay. So when we actually evaluate the limit, we plug 0 in for delta x. Our derivative is 2x. Yeah.
Is it always going to happen that the derivative is like one power less than the equation that you do?
Potentially. Hold on to that for now. All right. So now I want the derivative I want the slope at the point 310. So our derivative, I'm going to teach you another little symbol here. Okay, evaluated at 310. That bar, I don't know if you use that in like physics or not, but that bar means evaluate at. Would be 6. So our derivative is 6. The slope of the tangent line of 310 is 6. Okay? Is that the slope at the coordinate 2, 5?
No.
No, that is only the slope at the coordinate 310. Very emphatic, thank you. I appreciate that. Now, what if I actually wanted you to write the tangent line? Remember how we talked a lot about point slope form? This is where I want it. If our coordinate is 310, y minus 10 equals slope times x minus 3. Here would be the tangent line equation. Okay. Here I was nice and I gave you the coordinate 310. If I were to only give you x equals 3, you would have to plug 3 into the original to get y. You would have to plug 3 into the derivative to get your slope. Okay, so don't look at this. All right, so please be patient, but also be persistent when you are going through these problems, okay? I know that these are pretty algebra-intensive problems right now, the limit of the difference quotient, and you've done them before, but please be patient, okay? If you're not getting the right answer, because I know that you are checking your answers in the back of the book, if you're not getting the right answer, go back and check your work, okay? Make sure you're subtracting all of f of x. Make sure you are multiplying out correctly, okay? You will notice Unit 2 is pretty long, isn't it?
Yeah.
Unit 2 is very long. All right, we have 1, 2, 3 quizzes in Unit 2 and a 2-day test. All right? Yes. Because there are derivatives later in the book that I want to do with the other derivatives, and so I put them together. Okay? All right, have a wonderful weekend. Make good choices. Enjoy your 3 days. Woohoo!